welcome everybody. Thanks for joining me. We're going to take a look at the fun part of advanced TypeScript. And this is going to be an interactive coding session. There's a few slides in the beginning, a few slides in the end, but mostly I'm going to show you code, which is what we all like, right? So first a little thing about me. My name is Dante. I am a public speaker, of course, and a technical consultant at a company called AE in Belgium. I'm a .NET and C# developer mainly, but I also really like TypeScript. And I'm passionate about the software craftsmanship movement. And what topics will I cover in this talk? Well, for this I broke it down into two axes. Right? We have the fun and the useful axis. When something is not fun and also not useful, yeah, why should we care, right? So we're not going to cover anything that's not fun and not useful in this talk. When something is useful but not very fun, come on, guys, it's Friday. We're not going to talk about that in this talk, right? So this is something I can assure you. Now for the interesting part. If something is fun, but it's also useful, that's nice, right? So you're going to learn some advanced TypeScript techniques here, which are both fun and very useful. The way I'm going to explain those advanced techniques is going to be fun, but it's going to be slightly useless. I built Wordle fully in TypeScript types. And I made a calculator kind of thing in TypeScript types. So that's the two demos I'm going to show you. Basically, it comes down to this. I was really proud of something, and I wanted to show it off to you, and you can run away, so that's very nice. But it's also going to teach you something, so yeah, all kidding aside, you will learn about all of these topics today while exploring some fun stuff. We're going to come back to this later, but I think with this 2-minute introduction, we can go to the code, right? All right. Bear with me here, because this desk is quite low, and so typing is going to be difficult, but there we are. Can everyone see this? I'll maybe increase the size a bit. I have here, yes?
Can you change to light mode? Is it difficult for you to do that?
I'm not sure I can, because I prepared everything in dark mode, but maybe this room is, yeah, I'm not sure if my VS Code light mode is quite set up. So, oh, well, that will work, I guess.
Thank you very much.
Yeah, that's way more readable, right? So, I have here a result type, and it's an evaluation of a generic type, a Wordle type. And you can see there is a secret word here. Right, so I'm not gonna, I almost did it, but I'm not gonna hover over that because that's our secret word we have to guess with our Wordle game. And you can see we also have a guess here, which is just 5 dots placeholder. If I hover over this result type, you will see 5 blank dots, 5 white emojis. So that means none of the letters we guessed are correct. I hope everyone knows how Wordle works. You might want to rewatch this talk if you don't, and first play Wordle a bit. But we're guessing a word here. So for example, I'm going to guess water. If we hover over this result type, we can see, yay, the W is in the correct spot because we have a green dot. Great. We can also see that A and T and E are not in the word, so we don't have to mess with that. But the R is interesting, that's a yellow dot. So that means it's in the word somewhere, but it's not in the correct spot. And I have installed a VS Code extension, so I don't have to keep hovering, so I can just type like a comment and then point to this type and put a question mark, and then we have an inlay hint that shows this type in real time. So if I now say, oh, this was wrong, so maybe we'll guess wrong next. Oh, interesting. So the R that was at the end of the word, we put in second place, but it's also in the wrong position. And we also know there's an O now. So let's go for words. Right, so this is all TypeScript in compile time TypeScript, right? It's not running anywhere, this is just types. Okay, so we see that the D should be in the word, but it's not in this spot, so it should be here, so it should be world. And now we have solved this TypeScript Wordle puzzle. You can also maybe see that we are on line 32, and there's some blank lines, so to not spoil the solution. So this is actually a quite small Wordle type we built in TypeScript. But as to not overwhelm you, I will build up to how this is actually done. So I'll delete all this, and we'll start with an explanation of how this works. And for that, I have a implementation, a simple one, of this Wordle game in just regular runtime TypeScript that you all know. So how would we build this Wordle type, for example? We would keep a result array. We would loop over the word. Then we would keep track of the letter that we are looping over. We would look in the secret word what the index of that letter is. And if the index is -1, the letter is not in the word, we can put a blank dot in the result array. If the index is equal to the position we are checking, then that's great, that's a green dot. And in all other cases, the letter is correct, but it's not in the right spot, so that's a yellow dot. So this is regular TypeScript, this is not TypeScript, it's types, this is just runtime. And I'm using this example to build up to the actual type solution. So what do we need to achieve in our TypeScript types to make sure this works? First, these are the steps that we need to implement. We have to find a way to loop over a string. We have to find a way to keep count in that loop, find this index. We have to do an IndexOf function here. We have to do also a conditional check to check if the index is -1 and so forth. And then we have to keep this result array and keep adding to it, keep adding these dots to it until we have the full length array. And this is also written in a way, you could also use array.push and stuff, but this is written in a way that we can one-on-one almost map it to TypeScript types, because in TypeScript types, you don't have arrays, you have type tuples, and you can extend them with the spread operator. But we'll build up to that. Now, the only thing that is in this list that is quite a bit more advanced is this IndexOf function. We will also have to build that ourselves in TypeScript types to make sure this works. But luckily, this IndexOf function is actually also just looping over a string, keeping count in the loop, and doing a conditional check. So most of it we can do, like with these 4 things, we can make this work. And we're going to go through examples together. So first of all, for a conditional type, a type that is kind of like an if expression or is kind of like a ternary operator. Well, for that, I want to show the example of, for example, a not empty string type. And it's going to take in a string as a generic argument. And what we want to happen is this example. I think I called it non-empty string in the example, so I have to change it. But if we put not empty string of an empty string, then we should get never. And if we put not empty string of hello, then we just get hello. So it's kind of like a filter. And the way we do that in TypeScript is that we cannot check for type equality like this, for example. We cannot check if that is that, then do whatever. Because in TypeScript types can extend other types. They don't equal other types, and some types are assignable to other types and these things, but we cannot easily check for equality. But if we say that the string we pass in should extend the empty string, well, only the empty string can extend the empty string, so that's kind of also checking for equality. If it is an empty string, we're going to return never, and else we're going to return the string itself. Now, this never, you might have seen it, but maybe you don't really know why it's useful, or maybe you don't even know what it kind of means. I'm sure you're familiar with any. The any type is actually the collection of all possible types. Like you can assign any to anything, or you can assign anything to any. The only thing you cannot do is assign any to never. Because never is the empty set of types, almost. Never can only be assigned to itself. So you can only assign something of type never to a variable of type never. So for example, if I do const x, just runtime TypeScript is never, and I try to assign a 0 as any, even though in most cases as any would just completely disregard any types, we still get a type error here. Like any is not assignable to never. Only never is assignable to never. So this I can do. Right. So that is valid. And so to show you also that the never type is kind of like the empty set of types, I'm going to build a small type called impossible. And it's going to be a string and a number at the same time, which is, of course, not possible. That intersection yields an empty set. And so type of impossible is never. So that's what never is. It's just the empty set of types. It's the thing that remains after all options are exhausted. So that was a slight tangent to show you never. Maybe you know, maybe you don't know, so that's something. This is the first part of the puzzle we actually already have now, the conditional type. Just this ternary operator, and we can extend. But to show you what is possible in this conditional type, in this extends clause here, we can do a lot of fancy stuff. We are going to look at a contains type, and I'm first going to copy the examples. So we want to build a type called contains, and it does what you would think it does. It checks if a substring is contained in a string. So let's build that. I'm going to do this. Sure. Type contains of string, and yeah, let's put letter. We know it's a substring, but maybe it's easier with the letters like this. And these should both be strings, so we'll do extend string. You can put some extra restraints on this, so we make sure we can only pass in strings to this. And what do we want to check? This is not right, yeah. What do we want to check here? In TypeScript, we cannot do this contains check directly. We can only check if a type is assignable to another type. And luckily in TypeScript, we have something called template literals. So template literal types, actually. So we can check, I'm just going to write some pseudocode, like we can check if S extends some kind of pattern where L is included. So I'm going to, this is bad autocomplete. Some kind of pattern where L is included. This is not correct syntax, but we'll get to that. And if that's true, then we'll return true. And if that's not true, we'll return false. So true and false are also types in TypeScript, like you can have number types and string types and Boolean types. Well, template literal types sounds an awful lot like template literals we know from JavaScript and TypeScript. So we might use that one, and that looks like the backticks. And then we know that L should be in there somewhere, but it can be prefixed by any string, and it can be suffixed also by any other string. And this way we see that we are actually checking if this S conforms to a kind of template where L is somewhere in there. And that's what this type should do. By the way, the string type can also be the empty string. So if the letter is at the beginning of the string, this will also match. And we can see here, for example, this is now evaluating to true, and this is now evaluating to false. Nice. So template literal types, very useful. And they're also very useful to get information from a string, not only check if it's in there. So I'll keep this on the screen so we can draw the parallel. And I'll build a first type. So we get the first character out of the string. We try to extract the first character out of the string. First of hello should be H. First of the empty string should be never. Like there is no first character. Okay, type first of S. And S should extend the string, just to be safe. We can actually do this pattern again. Like this is good. We can check. But now we don't have this L here. Right? Here L was passed in from the arguments. Here we don't have it, but we want to extract it. And we want to infer it. And that's the hint of what we're going to use. So if we want to get something out of it, we can put here infer first, for example, or F, whatever. And now TypeScript will look at the S you pass in, for example, hello, and it will see if this could match the template you are referring to here. So it will see, does hello extend a string? Yeah, well, I'm kind of wrong actually here, so it should be this. Yeah, well, does it extend something that has a first character and then anything after it? And if it does, we're just going to return that F that TypeScript found. And if it does not, we're going to return never. So now TypeScript is inferring the F to be H, the character H. And then it's returning that. But if it cannot infer this template, like the infer keyword always has to match at least one thing, then it will return never, because this pattern is not extending. So now we can also extract letters and characters from strings. We can extract information from other types. Okay. This allows us, yeah, some nice stuff. Now the second thing we also need to learn that I showed you in the example is that we need to create some kind of a loop to check all the letters and just check the index and stuff like that. So how do we loop in TypeScript? Well, in that case, TypeScript is kind of like a functional language. So in a functional language, you don't really have for loops or stuff like that, but you have recursion. So this might take you back to your computer science classes, but we're going to dabble in recursion a bit. And for that, I am building a type called repeat. And repeat, all it should do is we're taking in some type, doesn't even have to be a string, could also be anything else. And it will repeat that type and put the result in a type tuple. A type tuple is kind of like an array, but yeah, it's a fixed length array of types where you can only, if you want to add one thing to it, you don't push to it or something, you create a new type tuple, but with stuff added to it. And that will be also shown later. So if I want to make this work, this repeat type, I write type repeat of t, and let's see how we are going to do this. So for recursion, we need a base case, right? To break out of the recursion loop, we need some condition that will break out. And in our case, we need a way to keep collecting these t's, these letter a's, for example, in the first example. We need to keep adding them to a tuple, keep making the tuple bigger and bigger, and once the length is the correct size, the length of the tuple is the correct size, we break out of the recursion. But we need to build that tuple. So we're going to have to also keep some state into our parameters here. So I will put an R, which will stand for result type. And this R will extend the array of t's. So we will build, well, I say array, but it's actually a tuple, right? But it will extend a tuple of t's, and it starts out empty. So you can have also optional arguments in generic types. So that's useful because, oh, I forgot the n, by the way, the number of t's we need to collect. Okay, so the R starts out empty. When are we done? When the length of R, this is quite interesting, no? You can take properties of types using square brackets. So we can get into the length of the result tuple, which is strange. You could also like index them. You could also get the first element, for example, by doing this. So quite advanced syntax there. But if you get the length of the tuple, and that extends the n that we pass in, so I say extends again, but kind of like equality. So if the length of the tuple we are building extends the number of iterations we want, well, then we're done. We just return this R. We're done building this tuple. It'll make sense later. And if it does not yet extend, well, then we're going to have to do recursion. Then we know we're going to do the loop again. So we do repeat again with the same type, with the same n, but we extend this result tuple, with an extra t. I'll put this a bit better. So, okay, so this might seem confusing, but if you see here, for example, we get the result we want. So what will happen in the first iteration, a and 3 will be passed in, but we don't have any, we have an empty array to start out with. Our length is 0. 0 does not extend 3, so we keep going. And we add another a to the array. So the array here was empty, but we add another a character. And we keep recursing until this condition is met, and then we have repeated ourselves. And we can also do it with 0, and then we get the empty tuple. All right. We've built a recursive type. We dealt with this. So this is the looping aspect of the solution for Wordle. We also needed the conditional types, which are also covered. But now we still need to find a way. So we have been looping, but we haven't like looped over the characters of a string yet. We just looped to build something or whatever, but we haven't looped over the characters of a string yet. And this one I'm not going to build from scratch, but I'm hoping with all the examples I showed you before, this is quite logical. In that case, if we want to get the characters of a string or the letters of a string, we check if the string has a certain template that it follows, the first character and then all the rest. So the infer keyword actually works in a non-greedy way. So it takes the first character by itself, and then it checks the next infer keyword, and in this case, the string ends at there. So then it can actually match all the rest that's behind that. But if I would put another infer, then first and rest would be both one character, and then the third one would be the rest of the string. So in this way, we use the first here to add it to the array. So we take one character from the beginning, we put it in the result, and then we keep the recursion loop, we do it with the rest. So we keep chopping up the first part of the string, adding it to the result array, and then we do the recursion with the rest of the string. So the string keeps getting smaller and smaller, and actually we're looping over the characters of a string. All right, quite theoretical, but it works. So. And with all this knowledge, we can now build the first piece of the puzzle, the IndexOf function. Well, function, generic type, actually. And so this IndexOf needs the string. It extends the string. We need a character, for example, that we're going to check the index of, or we called it a letter before, so I'm going to do that as well. That also extends the string. And then we need to keep this result array. This is going to be a pattern that's very common in this talk. We need to keep an array. So extends array of not t, but yeah. Now it actually doesn't matter what we collect in the array. We're just going to use it to keep the index. We're just going to use it to count. We're at iteration 1, at iteration 2, or all 0 first. But we just use it to keep an index. So it could be any array. I could put here an array of emojis, it doesn't matter. But I'm going to put an array of zeros just because that's one character and I'm quite lazy. So what we need to do for this IndexOf function. So we need to chop up this string into letters. We need to loop over the letters of the array. So we keep chopping the first letter off, checking if that's correct with the index, and then we return this index if we have found a match. So I'm going to copy what we did before as well, which is this. Oops, messed it up. I'm just going to put 0 or 0 so it formats for me. So we're going to do this pattern again, first and rest. You could also call it head and tail. That's often done in functional languages, but I prefer first and rest. And then we're going to just check again. So now we check if the first character we found matches actually the character that we want to check. If first extends the character, then that's fine. We found it. We can return the index. Now, what is the index of where we are currently in the recursion loop? Well, it's just the length of the array we are keeping to keep track of the index. So we cannot keep an I. We cannot do for I equals blah, blah, blah. We can, however, just add 1, 0 to the array and then use the length as a kind of index, which is a nice hack. So if that matches, we just return the index. If it doesn't match, yeah, we have to do the IndexOf again, but with the rest, right? So we check this first character, the letters didn't match, so we keep doing the loop with the rest, and then we also need L and R. But not just R, actually. We need to add 1 to R, 1, 0 to R, because yeah, we're in a loop and we keep track. And if nothing matches, I'll just format this so that's better. I forgot here my thing. Oh yeah, I put car here, but it's I'll, sorry. If S does not extend anymore, then we don't return never, actually we return -1, which is common in IndexOf function that you return -1 if nothing is found. This is half of the Wordle solution already. I mean, it might look quite complicated, but we have all the tools to do it. And then the only thing we still need to do, if you remember from the JavaScript code, TypeScript code, runtime code, is that we need to do this part, where we check this IndexOf, the result of the IndexOf, and we match it to see which dot we need to put. And I'm not going to bore you by typing that. I'm going to copy it and then just show you, because that's just like a simple, well, it doesn't look simple, right? But it's actually quite straightforward if I put it on here. Yes. So it doesn't look simple, it looks awful actually, but you see here we're just doing conditional checks, and here we're checking if this IndexOf, the result of it, extends the length. So again, the index of the loop we are doing here, if it does, then it's green because it's in the right spot. We match the index with the IndexOf in the word. And if it's -1, then it's a white dot, which is logical. And then just in all other cases, we put the yellow dot, because then we know the letter is in there, but it's not in the correct spot. And that's Wordle in TypeScript. It's like 21 lines. Well formatted also. You could put it maybe all in 2 lines, but I wouldn't recommend it. So what was actually the point of this? Well, that's a good question, right? It was fun, to me at least, maybe not to you. But we learned about so many things. We learned about conditional types, type recursion, template literals, stuff like that. But then I thought, well, we did strings now. What about numbers? Like, can we build a computer with TypeScript? Obviously, someone on the internet has already written Doom in TypeScript types. That's a thing. I think it was like 200 terabytes of types. Like, it was a huge, he had to compile his own TypeScript compiler because it would run into issues. And yeah, someone has done that. Look it up. But I wanted to do also some arithmetic with TypeScript, see what it can do. Can it like add 2 numbers? Can it like multiply numbers? So let's take a look. Can it do it? I think I know the answer, but. So let's start very simple. If we're starting to do math, we need a way to count. And luckily, we did it already with the strings and keeping the index. We just made an array of zeros and we counted with that. So I'm going to create that helper type that's going to help us later. Count of t, well, I'll call it n because it's a number. Extends number. And so if we pass in a number, we will just count result, for example. If I do count of 5, I want 5 zeros. Right. I pick zeros arbitrarily, right? But it's just an easy character to type. So if I do count of 5, I want an array of 5 zeros. If I do count of 10, I want... This is like the repeat example, but simpler, because you don't need to say which type you want to repeat. You just count. And it's the pattern we already saw before. It's this one. When the length equals the number, return the result that you have built up, and else we keep counting. Just do a recursion loop and add 1 to the array. And now we get what we want. By the way, this same mechanism is also already handy to do like a minimum check. If we want to do a minimum check of A and B, we just also keep a result array to keep count. Actually, yeah. Come on. Is empty first. And what we do is we count up, and once one of the 2, if A is matched, then A is the minimum, and if B is matched, then B is the minimum when we count up, because we count up, and then the first one we encounter, that's actually the minimum. So we can do this. So we count up, if the R is extending A, then it's A, and if R is extending B, then it's B, and if neither of those are true, then we keep just counting. We just also add another element to the array. So that's actually already very simple. We can do min result is min of like 3 and 5, and we count up and we recognize 3, and then, well, the min is 3. Okay, we can do minimum, that's nice. We can also do maximum by just doing the opposite. If we count up and we find A, we just return B. Well, that's a maximum of 2 numbers, so that's quite easy. But, tangent aside, let's start actually doing math. Let's increment a number by 1. How hard can that be? So I will type inc t. I'll use t. Why not? We'll increment t by 1. Right? So if I do increment 5, it gets 6. We can add stuff to tuples. So if we just use this t, which is a number, by the way, number to make sure we don't pass in something wrong. If we just yeah, we have to find a tuple now of length t. Luckily, we can do that. We have the count. So we count up to t. This gives us, for example, a tuple of 5 zeros. And the only thing we need to do is add one more. And now we have a tuple of 6 zeros, for example. But then we still need to convert it to a number, so we take the length of it. So this is the only thing you need to do to increase a number by 1. So if I do inc here and inc 5, yes, we get 6. All right. We can increment numbers. This is almost a Turing machine. So we can do anything. Same vein, we can decrement numbers. Is that possible? Well, we cannot do this trick anymore. We cannot take one element away. But in the Wordle example, if you remember, we used the infer keyword to chop off the first character all the time and then loop and then keep the rest. So what if we could just chop off the first 0 from an array of zeros and then use the rest and use the length of the rest? Then we have, we have taken away the first one and we have the length is then 1 less than what we started with. So in practice, this means we check if t extends an array of zeros, infer first, infer rest. So if t extends this pattern, so you can do it also with tuples. So we had done it with the string template type, but you can also do it with tuples. And this will also then match the first element of the tuple, and this will match the rest. So if that's the case, we just return the length of the rest. Because remember, I told you the first one is 1, and then it goes to the next infer keyword. So if I would put here infer middle, not really middle, but it would get, or 2, it would get, the first is 1, 0, the 2 is 1, 0, and the rest would be then 2 less than what we started with. But we need 1 to decrement. So we return the rest length. And if it does not extend, then it's probably 0, because then we're probably dealing with an empty array here. Why is this complaining? Oh yeah, we're doing t, but t is a number. So we need to count t, and then we get the tuple of zeros. And why is it still complaining? Length cannot be used to index type rest. This is strange. I might have, oh yeah. Something interesting, I forgot. I was thinking about the template literal types and strings, and then you don't have to do this. But with tuples, you have to actually show that you're inferring all the rest, which is a strange side effect. But so now, type dec of 6. No, dec is dec of 6. I am not good at typing today. That's 5. Increment and decrement. Yeah, this is very basic. Can we now start adding 2 numbers, please? Can we actually make a sum now? That would be great. So I'm going to do type add of a and b. Does anyone already know how we're going to achieve this using just increment and decrement? Anyone want to join in? No? So if we want to add a to b, what we can do is just loop until b is 0. And we just keep decrementing b and incrementing a. And so when b reaches 0, we will have incremented a b times. So we did add a plus b. So that's some kind of lateral thinking there. And it results in this type. So when b extends 0, we return a, because now we have added all the b's to a. And otherwise, we keep looping here. And this complains because somehow, I'm not sure why, this is a very strange thing. I'm not sure why. I encountered this before. If you do inc if you do this, like this says that inc a does not satisfy the constraint number. But the length property returns a number. So I'm kind of confused. What you can do is say, okay, I want the intersection with number, and then TypeScript shuts up. So we're just intersecting like a number with the type number, and now TypeScript knows, oh yeah, it's numbers. Oh, fine, yeah, nice. Weird. That's a weird quirk. I'm not sure why. If anyone else knows, I'm sure maybe also get YouTube comments about this. So So yeah, we keep incrementing A, we keep decrementing B, and once B reaches 0, we return A, and that's adding. We can do a kind of similar thing, I guess, to subtract numbers, no? Well, yes, we can. We kind of do the opposite. We keep decrementing B as well, but also every time we decrement B, we also decrement A. Now, I have to point out, this is not like negative number safe. I have a solution for that, but I think this would be way too boring to show. Like it's like a long type with, oh yeah, if this has a minus sign in front, like inferred from the string, I make the string of the number and then I take the minus sign anyway. That would lead us too far. But if we do 5 minus 3, yeah, we get 2. That's nice. How are we on time, actually? Because I can go on forever. Okay, still 20 minutes. Then I can show you multiplication as well. How are we going to do multiplication? That sounds strangely more difficult. Because now we cannot just increment and decrement, because, yeah, we need a multiplication type of A with B. And now we're actually having to keep a result. But the result can just be a number. I will start out with 0. And what we can do to multiply A with B, we can just also decrement B all the time and keep adding A to the result. And then we will have added A to the result B times. A times B. Nice, okay, let's do that. So I'll build this out from scratch again. So we'll have to check first if we're done. If B extends 0, right? If B extends 0, then we return R, because then we have added enough A's to R. If that's not the case, we do the multiplication again, but we keep A, we decrement B, because we've done one pass, so we can decrement B by 1, and we can do add of R and A, because we need to add A to R B times. I'm starting to sound like an insane person, but I hope it makes sense. Am I doing something wrong still? Yeah, probably keep TypeScript happy by saying these are all numbers. Numbers, no number. And now I also have to say that this is a number and not just a 0. And I call it molt and not null. Yes. And so now if we take the result of 3 and 5, we get 15. Yes. Nice. All right. So this is starting to become like almost a small calculator. Now I had demos for division and modulo operators and stuff like that, but I think we'll cut it short a little bit. Well, maybe you want to see them, no? Division. Okay, well, great. Division is quite complicated because you have whole division, 15 divided by 3, that's quite easy. But you also have like 17 divided by 10, which is then 1 with a remainder of 7. Or is it just like 1? So we'll start with whole division, just plain and simple. Well, it's not too simple, but we'll start just simple with 15 divided by 3 should be 5, right? So I'll make a type whole division of A and B. So same pattern always repeating. We're just gonna, how are we gonna do this? Right. So division is kind of like asking how many times can we subtract B from A until we get A to 0, right? So 15 divided by 3. How many times we can take off a 3 of 15, so first it's 15, then 12, and how many times we can do that until we reach 0. And then we know how much division we have. So we're going to keep as well a result that extends a number and it's 0 at the start. And how many times can we do it until A is 0? Thus when A returns is 0, then we can return the result. And if A is not yet 0, we still need to take away a B. So we do whole division again with A, not with A, with A minus B. So we take away one B from A, we keep the B, and we take away one B, and we increment the result by 1. I hope I'm making sense. And otherwise, you will probably not tell me. So that's nice. I can assume. Not 0, number. Oh, I'm messing up here. Number. Nice. Does this work? Yes, 5. Great. So this looks amazing. Like, so we keep subtracting b from a. We keep using the same b all the time, and we keep incrementing the result whenever that works, and until a is 0. So that's whole division. If you want to see division with remainders and stuff, then what I actually do is I calculate the division, the whole division, and I multiply the whole division result back with the original b, and if that gives me the original number that I put in, then it's fine. If that doesn't, I'll just decrement the result by 1, because I know I went 1 too far. And that's this one, if you want to see this. Multiply the result of the division back with b. If that is a, then nice. And otherwise, yeah, decrement the result by 1, because you've gone 1 too far. And similarly, you have the modulo operator. I'm just going to not explain it from the start, but it's quite simple. This seems very nested, so I will put it in like a more mathematical notation above it. The modulo of a mod b is kind of the same as dividing a by b with whole division, then timesing it by b again to see what you get, and then see how far away you got from a. And then you have the remainder. So that's kind of what we do here. Right, enough maths. I think we're all cooked. You just had lunch. So let's go to the conclusion. Quick breather. All right, the code is finished now. So what you've learned, I showed this in the beginning. You should now, I hope, recognize all the terms that are on here, and we should have seen them. I don't think I covered union types though, but I covered the intersection type with the ampersand. And so when is going this advanced actually useful? Because I was showing these examples that were quite useful, but the techniques are quite useful. The examples were quite useless, actually. But the techniques are quite useful. And when do you need to go like this advanced? Well, mainly for writing library code. If you need other developers to use your types, then it might require some quite advanced techniques to make sure they're locked in. You can see it, for example, here with the styled components library. If you put in a color, then you get all these options, and you get nice developer experience. You get type safety if you put something wrong in, and there will be a red line underneath. It prevents also runtime exceptions, if you know what a certain variable, which type it can be at a certain time. And if you change something, hopefully you get like a red line if you change something the wrong way. And you can use the IntelliSense that your IDE uses as documentation. If this would just be a string type, you would like be lost. What can I put in there? And now you can just like control space or something, and you can see the whole list. So this is quite useful when writing library code, not only for open source libraries, but within your own company. If you write code that other people use, or you write utility types, this is very useful. That being said, like, you can make anything in your job quite useful. But like on the left side here, this was my solution for Advent of Code 2 years ago. So one of I think day 1, I wrote this horrible thing, which solved it in TypeScript types, completely like in compile time TypeScript. And if you don't know, Advent of Code is like this cool programming puzzles that people do mainly for fun. You can do them in any language. So I felt kind of challenged to do it in TypeScript. I had coded the examples I've shown you before, so I was not like from scratch. But I learned a lot in the process of doing this. And I also had a lot of fun, actually. And maybe yesterday you might have seen the talk by Lucky in room 1, where he flew a drone controlled by bananas. It was amazing. And that actually reminded me of the message I wanted to bring to you today. Like, his message was almost the same as mine. Like, keep coding just for fun. Beware, you might actually learn something. It actually helps you learn something, and it actually helps you improve even though you're doing stuff like building Wordle in TypeScript. And with that, I think we're done. I want to thank you for your participation in this. I want to thank you for letting your brain be melted and enjoy the rest of the conference. Is there any questions? I think we still have some time, lots of time actually. Yes, I see a question.
A quick one for the add. Could you have just spread the count of the two numbers, or would that not have worked?
I guess so. Let's try it out. That's a good suggestion actually. Add a, oh, I put it before, so let's just replace this then. So like this probably, count a. So for people that didn't hear, could I just do this for add, just spread the two counts? That would actually be a very simple solution, probably, if that works. Length, if I can type. Now it complains again that it's a duplicate, okay, because I've typed it here. Okay, I thought it was going to complain again that it's not a number. Look, it does here. So taking the length, even though it's a number, it's not a number. Right, okay, number. That should work, right? Type add is add 3 and 5. Genius, yeah. You get a gold star. Great, okay. Nice. Anyone have any other questions? Well, thank you. Oh, there?
Yeah, what happens if you do something extreme by accident, like a negative number or a fraction?
What happens if I do, for example, subtract 3 from 5? I think we will end up at 0, because once b is at 0, it just returns a. So maybe I tried this, but I forgot what the result was. 5 by 3. No, 3 by 5. Yeah, I think you just get 0. Yeah. Let's figure this out. So if b extends 0, then we return a. So we keep decrementing b. But that's actually strange. No, you just get 0. Well. Anyone else? Yes?
What happens if you try and divide by 0?
Will it explode? You just want to break my code. Oh, come on. Oh. Loading. Well, it actually does what you're expecting it does. Like it's breaking all the time. Yeah, loading. Something else that's interesting, for example, if I try to count, I hope I don't break my VS Code now. That's still evaluating the type. But if I do a count of 999, for example, then yeah, it will load a long time, but it can do it. But if I do a count of 1,000, then TypeScript will complain. What? It complains for a different reason now, but sure. Oh yeah. Can I find name? Okay, now it's just like doing this, I guess. Oh yeah, this is the same error I wanted to show you with the count of 1,000. Type instantiation is excessively deep and possibly infinite. So in this case, it is possibly infinite because it just keeps going. In this case, it would be excessively deep, meaning more than 1,000 or more. So TypeScript doesn't like recursion loops of more than 1,000. They hard cap it. The man who built the Doom in TypeScript types, he wrote his own compiler to also circumvent this limit. So yeah. Good questions, good questions. Anyone else? Well, then enjoy your Friday afternoon and thanks. Bye.